So in this video, we're going to continue with chapter 3 and talk about sections 3.2 and 3.3 if time permits. So this section 3.2 is dealing with the states and the properties of matter. All right. So there's basically three states of matter. There's solid, there's liquid, and there's gas. Okay, so we'll define each of those states of matter. So solids have definite shape, they have a definite volume. Okay, and this is because if you look at the solid right here in this picture, you can see that how closely the particles are packed together. All right, so solids are pretty dense because the particles that make up the solid are packed very tight. And there's very little room for movement. All right, so the particles are vibrating in their fixed position. So the positions of those particles that make up the solid are fixed, and that's why they have a definite shape, as well as the definite volume. Okay, so these particles, if they move at all, it's very slow, or it's kind of just in position. Okay, now in a liquid, you can see there's a little bit of more space between the particles that make up the liquid. This is water. And so that allows for room for movement, so that allows room for flow. All right, because there's a bit more space. So liquids maintain definite volume. That means if I take this volume of liquid and I pour it into a larger container, all right, whatever this volume is, that's maintained. So for example, if I had 5 mils of water in a beaker, and then I took the 5 mils and poured it into a test tube, it'll still be 5 mils. However, the shape will change. All right, just like if I take this and pour this into a square container, it'll take the shape of the container. All right, so indefinite shape but definite volume. All right, here there's the particles are not so close, so there's a little bit of mobility. All right, that mobility allows liquids to flow. Okay, now gases neither have a shape or volume. All right, gas particles themselves are very tiny, so they just spread out and occupy any container in which they are put in. All right, so for example, this balloon, you can take the same amount of gas and put it into a different container, and it would occupy that entire container. So most times when we talk about gas volumes, we are talking about the volume of the container rather than the gas, the aggregate gas particles themselves. Okay, so they take the shape of whatever container they are in, and they have indefinite volume. All right, so this same amount of gas, I can take it and put it into a large cylinder, and it would occupy that entire space of the cylinder. All right, so gas particles are very tiny, they are very far apart, they move a lot because there's so much space. Okay, so you can think of a gas as being nothing but a lot of space. So to summarize, the solid has definite shape and definite volume. Particles are kind of fixed in space inside that solid, very close. The interactions therefore will be very strong. Movements are not much. They vibrate in place, and that's about it. So some examples would be ice, salt, iron, etc. All right, anything which has a solid shape at room temperature. Liquid will take the shape of the container, definite volume. The particles are close enough, but not that close. There is a little bit of movement, a moderate amount of movement, which allows the liquid particles to flow past each other. All right. Interactions are kind of strong because they are still kind of close. All right. So anything that is liquid at room temperature, water, oil, vinegar, tea, once you make the tea in water, of course, and so on. Gas is takes the shape of the container, and it doesn't have a definite volume. It It just fills up the container in which you put the gas in. The particles are very far apart, and so the interaction is essentially none. There's zero interaction between the particles, and it's very fast. The particles are in constant motion and moving rapidly. So anything that is oxygen, air, nitrogen, helium, water vapor, anything that is in gaseous state at room temperature would be examples. All right, identify the following as a liquid, a solid, or a gas. Definite volume takes the shape of the container, so that would be L, liquid. Particles are moving rapidly, that would be G, gas. Its particles fill the entire volume of a container, that would be G, gas. Its particles have a fixed arrangement, that would be S, solid. Its particles are close together but moving randomly, so that would be a liquid. Identify the state of matter for each of the following: vitamin tablets, solid; eye drops, liquid; vegetable oil, liquid; candle, solid; air in a tire, gas. So physical properties are what you can observe by looking at something, all right, like the color, the shape, the size, the state it's in, its boiling point, freezing point, its density. All of those are physical properties, okay? Because you're not chemically manipulating it, you're simply observing it as in the state in which you look at it, all right? So, for example, if you're observing these copper vessels, what you see is that they're reddish orange in color, shiny. They're good conductors of heat and electricity, which is why they're cooking vessels. They solid at room temperature, and then if you try to determine the melting and boiling point, you'd be able to do that, provided, of course, you have a furnace, because as you can see, the melting and boiling points are so high. Okay. A physical change is when you are doing something to matter where you change its state. So going from solid to liquid, like melting ice, or liquid to gas, like evaporating that liquid, or changing its shape, in the sense, when you cut up a piece of paper, you're changing its shape, all right? It's still paper. The key here is physical change doesn't involve anything that changes the identity of the substance. So for example, when I boil water or melt ice, the chemical identity is still H2O, it's still water, all right? It might exist in different phases, but it's still H2O. So the identity and the composition is not changed during a physical change. So water boiling or sugar dissolving into the water, you can separate out the water and the sugar, because you can evaporate off the water and then you get back your sugar. Copper being drawn into wires, again, you're not changing anything chemically, all right? It's still copper in those wires. Paper being cut into shreds, that's again just changing the size. Pepper being ground into flakes, again, you're changing the size but not any kind of chemical change or composition. Classify each of the following as a change of state or change of shape. Chopping a log into kindling, that would be change of shape. Water boiling in a pot, that would be change of state. Ice cream melting is change of state. Ice forming in a freezer, change of state. Cutting dough into strips, change of shape. So So chemical properties, on the other hand, you're looking at how things are interacting, all right? How a substance is interacting with another substance. And then what happens during this interaction is that a new substance form, all right? So you're looking at chemical reactions between substances and the resultant change that happens, where you get a new substance, a new identity. It has new chemical and physical properties, all right? It's no longer the original substance. So something like a chemical change, for example, is caramelizing sugar, all right? So it's no longer sugar when you caramelize it. It's chemically undergone a chemical change. Bonds have been broken, and it's now a new substance. That caramel is no longer the original sugar. It's different in its chemical and physical properties, and it also has a new composition. Okay. So shiny silver, it reacts with air and you get a black residue on the silver where it tarnishes. So it used to be silver, now it's silver sulfide. So that's a chemical change. Piece of wood is burning and it's becoming ashes, carbon dioxide, and water. So it's no longer wood, all right? It's no longer the chemical composition of wood. It's broken down and new substances are formed. Heating sugar to form caramel, all right? Again, that sugar chemical identity has changed and it's become a different substance. Iron combining with oxygen and rusting. So iron was just Fe, and then rust is Fe2O3, all right? So that's a different chemical compound with a different chemical composition compared to the iron, which was just iron atoms. Okay, classify each of the following as properties as physical or chemical. Ice melting is physical. Copper is a shiny metal, that's physical. Paper can burn, that's chemical. A silver knife can tarnish, that's chemical. A magnet removes iron from a mixture, that's physical. Classify each of the following as physical or chemical. Burning a candle, chemical. Ice melting on the street, physical. Toasting a marshmallow, chemical. Cutting a pizza, physical. Iron rusting in an old car, chemical. Temperature. So you can see here nowadays you can use these digital portable thermometers to take temperature, and the temperature is more like a feeling, all right? You're feeling how hot an object is or how cold an object is. So what you're measuring is mainly the heat flow, all right? So for example, if this temperature is registering the temperature of the surrounding air, all right? So then the heat flow is from the air to this substance, the alcohol in the thermometer, all right, which is why you're registering it as a temperature, all right? So temperature is kind of like a feeling of hotness or coldness of an object, okay? Now, some of the key temperatures to take a note of is body temperature, which is 37 degrees, and the equivalent is 98.6 on the Fahrenheit. If you go below 36 degrees centigrade, that leads to hypothermia, all right, when you become really cold. If you're out in the cold for too long on a very, very cold day, okay, you can develop hypothermia. If it goes above 37, then of course that's called as fever. And if it rises up to 41 and above, that's hypothermia. That could eventually lead to death. Okay. So the temperature scales are Fahrenheit, degrees Celsius, and Kelvin. Okay. And they are taken with respect to the freezing and the boiling point of water. We'll stop here and continue this in the next video.